fast. We are going to start in 2 minutes.
Guys, please take your seats quickly. The talk will begin shortly.
Start. There are people coming, they will be coming.
उनका टाइम जा रहा है तो कैसे मेरे को वो लग रहा है एक बार बोल दे गाइस सेटल डाउन
हो गया यार, ठीक है, बोल दिया।
हेलो।
I'll start talking, they'll be joined.
Welcome to the public lecture on the occasion of National Science Day at TFR. Today I'm honored to I think you should start.
Hello everyone. Welcome to the public lecture by Professor Sriru Prai Chaudhary on the occasion of National Science Day. I'm honored to introduce him. Professor Sriru Prai Chaudhary works on the physics of elementary particles and their interactions. He's a PhD from University of Calcutta and then worked as postdoc first at TIFR itself and then at CERN Geneva. He taught physics at IIT Kanpur for several years before joining TIFR, where he is now a professor of theoretical physics and dean administration. His research interests are interfacing theory with experiments, especially in the physics of electroweak interactions. He is also interested in popularization and history of science. Today, he is here to tell us the story of particle physics. So let's welcome him with a huge round of applause.
नहीं इसमें पानी का Good afternoon, everyone. So, first of all, let me thank the organizers for inviting me to give this talk, and also my young friend for this nice introduction. So, today, what I will be talking about is the final frontier, which is going to be the story of particle physics. And this talk is not going to be technical. Particle physics can be very technical, but today's talk will be more like a storytelling. So let's, without further ado, let's start the story. So here is a map of the world in 1774. That's 250 years ago. Can we have this light off, please? So, as you see here, there are large white patches on this map, white patch here, and it said undiscovered. So at that time, we didn't know even the world which we live in. Now, let me cut and come to 2024. That is your world map. Every part is well mapped. There is a country everywhere, well defined, members of the United Nations. And moreover, if you want to look at details, you can look at Google Maps. This is, for example, our new Trans Harbour link in Mumbai. And if you want to go and see how Mount Everest looks like, you can also see that. This is Mount Everest, Khumbu Glacier, and you can look at all the details of these. So the question is, can we, how well do we know our world? Do we know our world well? Well, let's look at it from a different angle. No? So we certainly know it well at the scale of houses and trees and streets. Well, what do you see? You see a bed of flowers. You can go outside and see similar beds of flowers here. So let's go a scale smaller and zoom this by about 10 times. So now what do you see? You see more details. You see the flowers in detail. You see some of their petals. You see leaves and so on. Let's go another 10 degrees bigger. And now you discover that there is a small insect sitting in the middle of one leaf, which I hadn't seen earlier. Let's go another step bigger. And now you can see the body of the insect and you can see its big eyes, again, which you cannot see with the naked eye. Let's go a step, another 10 times bigger. And now you can see the details of the eye and you see that it's a compound eye with these little eyelets. Let's go bigger, or smaller rather. And now you can see the detailed structure. And you see these little filaments. These are what the insect uses to sense direction. Now, we can go further. Let's go 10 times bigger. And now you can see the details. This is where these filaments grow from. There's a little bit pod, and these are the eyelets around it, and there's a bit here. Let's go further. And now you can see that this filament itself has structures, and there are little of structures below this also. Go a step more, and you can actually see the protein fibers which build up that filament. Now, this is about as much as we can take pictures of. But if you go beyond this, you will end up by seeing that you will get the DNA helix inside the protein fibers and the cells inside them. Go even further, and now you will see atoms. There are atoms inside the DNA. Go further, and in the center of the atom, there's a nucleus. And now go right into the nucleus. There are protons and neutrons, and each proton or neutron is composed of 3 different particles called quarks. Now, this is the limit of what we know. If you want to go beyond this and look at smaller scales, smaller things, then that is the realm of speculation or of discovery. And this is what I call the final frontier. So the final frontier is not anymore places on the earth, but it is places within. So within us, within every molecule, within what I'm holding, within every chair and everything else we see around us. All right, so you may ask this question. I've told you a lot of stories. Why should you believe me? Okay, how do you know that any of this is true? So let's begin this. It's a long story, and good stories should always begin at the beginning. So let's go back right to the beginning. So long before the dawn of written history, humans began to manipulate the natural world, okay, by changing things, by making tools, by making little houses, making little dwellings. So before long, they discovered that if you take a hard material, you can grind it into powder. And this is an object which is 7,000 years old. It was found in Oman. And what is this? This is your humble mortar and pestle, okay, what you use in the kitchen to grind masala. Same instrument, not too different today. And using this, let's look at what happens. See, this is a lump of coal. Okay, well, not so popular in the household nowadays, but earlier you could go to your house and pick up a lump. Now, suppose you grind the coal, you will end up with a lot of little pieces of coal. However, if you zoom into this, you will see that it consists of little pieces of coal, which are sort of similar to the previous bigger piece, so small pieces of coal. However, you can grind that up further and you can get a finer powder. But again, if you look at that with a microscope, you will see that every little piece is just a small copy of the bigger one. So you can ask this question, where does this, how far can I go on grinding to smaller and smaller pieces? Now, on another track, very early people realized that if you take different substances, you can, convert them by heating, warming, cooling, and stirring. You can convert them into other substances. You can take a bunch of substances and make it other substances. And your mother does that in the kitchen every day. Okay, making some substances, putting them together, and making it into a tasty substance for you. Now, but perhaps it was an ancient metal worker, the first people to discover metal, who first speculated that some substances might be more fundamental than others. Some substances obviously are obtained by putting other things together. But where does that stop? What are the most fundamental substances? And there, this started a great quest for answers to two fundamental questions. The first and most important question, what is everything made up of? And the second part of that question is what makes these entities act upon each other? So what makes them come together and form bigger structures? So these are the two aspects. And in the broader sense, this is the understanding of what I call particle physics or elementary particles. So what is the most fundamental things and how do they come together? So we will now, our story will be about how this went on. So I will start by reminding you that Western science had its beginnings in the speculations of the Greek philosophers. So Greece is a small country at the south of Europe, and the Greeks in the early days used to live somewhere, some in this part and some in this part, which is now Turkey. And I will apologize at the moment because I will talk about Greece only. There were parallel developments in Egypt, in India, in Iran, in China, and so on. So I don't have scholarship to talk about those. But I will talk only about the Greeks in this talk. So a Eurocentric version, if you like. Now, these Greeks had a passion for unification. They didn't like the fact that there are so many different substances around us. So it started with Thales of Miletus, who thought that water is the most fundamental substance. He said, okay, water freezes into ice. It can be boiled into steam. It must be the most fundamental substance. I'm not sure how he came to this conclusion living in Greece. If he had been in Antarctica or in Greenland, perhaps it would make more sense. But now he had this, perhaps it's because Miletus is by the seashore and he loved to bathe in the sea. Anyway, but Greeks were argumentative people. So another Greek philosopher called Anaximenes said, no, it is not water, it is air. Okay, air becomes condensed into water, and so steam is the most fundamental. Air condenses into water, into solids, and so on. Now then came another Greek philosopher, another wise man. He said, no, it is fire. Fire is the most fundamental thing, and fire condenses into things. And of course, the retort had to come. And the person says, no, earth is the most fundamental thing. Solids are the most fundamental. So Greeks, as I said, they like to argue. They didn't like to do things with their hands. So each of them argued for their hypothesis. Sometimes it was one winning, sometimes it was other, depending on how well they could argue. But then, along came a person who was like a statesman who managed to put all these different schools together, something like India Alliance. So he said, okay, all four of them, you maintain your own character, but they are all four elements. And this was Empedocles. This is known as the doctrine of the four elements. Now, we have the similar doctrine in India of the Panchabhuta. So what happens is that all of these together are mixed up, and that's what mixing of these creates all the substances we see around us. Now, notice the important thing here. What is there then? All substances are mixtures, and it is the proportion of each of them which gives you different substances. So how much of fire is there makes it, let us say, hot to taste. How much of water is there makes it cool, and so on. How much of earth makes it hard. So this idea that it is these proportions which create the different substances means something, that the multiplicity of substance we see around us is now replaced by multiplicity of these proportions. And since mathematics gives you any number of fractions you like, so you have replaced the fact that you have all kinds of substances around us by only a few substances, and the rest is all different proportions. So the multiplicity is that of mathematics and not of reality. So that was the idea, and you will see that this idea keeps repeating and even into modern times. All right. So this theory, by the way, still survives not as four elements, but as four phases of matter. So instead of water, we call it the solid phase, liquid phase. Instead of air, we call it the gaseous phase. Instead of earth, it is the solid phase. Instead of fire, we call it the plasma phase. So there are four phases of matter which correspond to what the Greeks saw. Now, Aristotle, who was the greatest thinker of ancient times, he accepted this doctrine of four elements. And because he accepted it, his immense authority helped this theory last till well past the Renaissance, well into the 16th century. So very rarely has a theory lasted for something like 1800 years. But it did. Now, there's a problem with this. It also gave rise to the spurious science of alchemy. How did that happen? The point is that if everything is made up of a mixture of these four elements, then so are precious metals like gold and silver. So all that you need to do is to find out the right proportions. Which is the correct proportion, let us say, which gives you gold. Mix things in that proportion, and okay, you made gold in the laboratory. So you made your gold, and now only cast it into coins, and you have become rich. So this is spurious science, and the alchemists never really succeeded in making gold because the theory is wrong. But what they did was they were able to find all these basic processes which you do in the laboratory, decantation, filtration, distillation, and so on, which are still used in the chemistry and biology lab. So all the things you do in the lab, these were processes were discovered in the chemistry, were discovered by the alchemists. So they had some use after all. Now, towards the end of the Middle Ages, some of the better alchemists, people like Albertus Magnus, Paracelsus, and John Dee, were realizing that some substances like mercury and sulfur, you couldn't synthesize them by mixing other things. I mean, they always came out separately. But they didn't go ahead and declare it. First of all, they were held back, first of all, by respect for Aristotle. In those days, it was dangerous to contradict Aristotle. And of course, they also wanted to make gold, right? So greed for gold also mattered. So they actually hoped to make gold. So it was left to... So here is a painting which today would be a cartoon, but in those days it was painted. Here is an alchemist who just thinks he has discovered gold, but all he has discovered is phosphorus, which is a good discovery, but not the same as discovering gold. So it was left in 1677 to Robert Boyle. So Robert Boyle was the son of a lord. He had lots of money, so he didn't worry too much about making gold. So he wrote this book, which in the language was known as The Skeptical Chemist. Forget about the rest. And there he said, this is the language of those times, it may likewise be granted that those distinct substances, let's read it in modern language. It may be defined that those distinct substances, which can only be obtained by the breakdown of other materials or be used to synthesize new materials, are the elements or basic ingredients of matter. So he was very clear. If you can't break it up further, it's an element. And the elements he defined at that time were mercury, sulfur, phosphorus, iron, copper, gold, silver, and a couple more. A couple more which are actually not elements. So that was good. Now, so these were the elements at the time of Robert Boyle, and other elements were discovered one by one. So almost every year, people discovered one element after the other. It's a long list. They kept coming. Okay, kept coming all the way till 1940, where astatine was discovered. Now, after that, people have been creating new elements, and that has been going on. And the last one we had was in 2010. So maybe there will be more in the near future. So today we know of 118 elements. So what the Greeks had started with, okay, became nice. First they had 4 elements. Then Robert Boyle and others said, okay, there are not 4 elements, but a bunch of elements. But that number has gone to 118. It is still less than the number of substances we see around us. But still, 118 is not a special number. In fact, it can increase. So then what are the elements? So we have still seen that there is something. It's not quite the answer. Well, even among the Greeks, everyone was not satisfied with this doctrine of 4 elements. There was a gentleman called Democritus who said that no, the elements are not. there are only atoms. Atoms are very minute particles, and they are all composed of the same substance. Remember, substance is the same. And there is this famous statement attributed, in reality, the only atoms of the word, everything else is opinion. Now, this is a very polite translation of the original Greek. If you were to translate it, let us say, into Hindi, then the word for opinion would be bakwas. Okay. So he said, only my idea is right, everyone else is wrong. And actually, that is the truth. So later his disciples said, okay, there are these five solids, basic solids, and the shape of the atom. This is the shape of the atoms of these substances, earth, water, air, and fire. You see, again, they're trying to reconcile different ideas. And so, if it's earth, then these cubes all sit in solid things. But if it's, let us say, an octahedron, then they sort of roll about each other, so it's not so strong. So the idea was that these different shapes are what gives rise to the different things, elements you see around. And therefore, again, this atomic hypothesis is basically a model of unification. Why unification? Because all atoms are made of the same substances. The same substance makes up all the atoms. And therefore, different substances appear different only because of the different shapes of the atom. So now you see multiplicity of substance is replaced by multiplicity of structure. Okay, not multiplicity of arithmetic, but multiplicity of structure. So you see, you will find that the same idea keeps repeating. Now we make a jump and we come to Sir Isaac Newton. How can you have a physics talk without Newton? So Newton was the first person, this is not well known, that he is the first person to start doing quantitative measurements and precise measurements in chemistry or alchemy of the time. So he probably thought that just as he has brought mathematical order to physics, he could do the same in chemistry. It turned out that he wasn't such a skilled chemist. So the result is he wanted to answer this question. Do the masses of elements entering into a chemical reaction satisfy mathematical relations? And he couldn't find those relations. Okay. So nevertheless, the question remained in people's minds, and it was others who answered the questions. You have heard of them. Lavoisier discovered the law of conservation of mass. Then Proust discovered the law of definite proportions, that the masses of elements are always in the same definite proportion. Then Gay-Lussac discovered the law of multiple proportions. So masses of one element combined with definite are in the ratio of small numbers. This is very important. And finally, Richter discovered the law of reciprocal proportions, which are, you study these in school. So what all of them told us, that when atoms combine, they combine in small ratios of small numbers. And this are called the laws of stoichiometry. Now, this immediately led Dalton to conclude that therefore they are atoms. So what is combining are atoms in small numbers. And of course, this is the famous atomic theory of Dalton. So what did Dalton say? Every element is composed of individual particles called atoms, but when atoms combine together, Avogadro told us that they're composed of molecules. Okay. Now, how do atoms combine in different ways? They have valence. So valence, you can imagine like little hooks on the atom. That's not literal, okay? It has to do with the electronic structure. But valence replaces shape. Instead of sitting together because of their shapes, they're combining together because of the valence. And so you see that now the combination property replaces what you had earlier called shape. So multiplicity of substance is replaced by multiplication of combination modes. And of course, the properties of the elements are not random. First, it was discovered in 1862 by Deschamps that if you take the elements and you put them on a helix, okay, take a helix and you keep putting on the elements around it, then similar elements fall one below the other. Okay, that was an interesting thing. And Newlands, he found that after every 8 elements, you seem to be getting the same behavior. So he called it the law of octaves. And he likened it. So he said it's very similar to the octaves in music. Okay. And the result was that he shouldn't have said that because people started laughing at him. Okay. They said he thinks substances are made of music. And the result was that nobody took him seriously. It was not till the periodic table came with Mendeleev, which was another 20 years in the future. And of course, with Mendeleev, the reason why people believed him so seriously was that he predicted new elements. So one of those new elements, okay, this is Niels Bohr who created the table which is this particular shape. But Mendeleev predicted this element, scandium. He predicted all its behavior just by looking at what it sends above or below. Then he predicted gallium, which is like aluminum, and germanium, which is like silicon. And over the years, people have been discovering other elements, as you know, but each element, when it was discovered, it fitted very nicely into one place in the periodic table. There's no element we have discovered till now which doesn't fit into the periodic table. So that's the discovery we have today. So, okay, here are the modern ones also. Now, I should come back to this. See, when you have a repetition of properties, that repetition indicates that there is some substructure. If something is repeated, something inside must be repeated. Otherwise, why is it looking the same? So let's see how far that hypothesis takes us. So let's ask the question, is the existence of atoms confirmed? So how do you know that the people from the past lived? Okay, how do you know your own great-grandfather lived? Well, we have photographs, right? Like we have this famous photograph. How do we know people live? We have never met them. But we know there is this photograph telling us that they live. So similarly, we have photographs of atoms. You can actually photograph atoms. See, here are two atoms bound into a molecule. So when you have a photograph, you believe it. Okay. Now, let's ask the next question. See, atom, the Greek word atom means indivisible. Means it can't be divided any further. And that was also the nature of the atom of Dalton and other people. So let's ask the question, are these atoms really indivisible? And that takes us to a little bit of experimentation. So in the 19th century, it became possible to create high electric voltages using induction coils, which were then called Rumkov coils. So this is essentially a transformer, but since you didn't have AC in those days, you used a make and break circuit to introduce high voltage pulses. Essentially, if you change the flux very fast, you get a large EMF. So with these Rumkov coils, people started passing electricity through gases which were very rarefied. And here is an example of an experiment done by William Crookes. Here is the Rumkov coil at the back. This is an evacuated tube with mostly vacuum inside, a little bit of air. And there are rays coming out from the cathode. And you see that if there's this cross, then you get this shadow. So this shadow, when you see shadows, you know that light travels in straight lines. Similarly, when you see shadows cast by these cathode rays, you know that these cathode rays travel in straight lines. Now, the cathode rays are also, you can deflect them with a magnetic field. So that's not characteristic of things like light. Light you cannot deflect with a magnetic field. So that means they are streams of charged particles. So you knew that much. Now, Sir J.J. Thomson wanted to study this deflection quantitatively. So this is the apparatus set up by Thomson. And I'm proud to tell you that I've taken this photograph myself. It is in the Cavendish laboratory, preserved at Cambridge. It's preserved there. And this is the real apparatus. Of course, this is a photograph of Thomson. Is no longer there. Now, what was in this apparatus? Let's see what the experiment was. So here you have a cathode. Okay. So when you put charges inside, the cathode heats up and starts emitting electrons. So electrons come out from there and they come and hit the glass here, you see. And when they hit the glass, it creates a fluorescence in the glass. The glass glows green. So from this green patch, you know that the cathode has come on. Now, if you put an electric field like this, you find that they are getting deflected and the whole patch moves downwards. Of course, it's opposite to the electric field, so you know that these cathode ray particles are negative in charge. You can also put a magnetic field across by putting, two magnets, and then you can bring it back by tuning the magnetic field or with electric field. You can tune it back so it comes back to the same place. Now let's take this distance to be r, and it's easy to show that when forces balance, you have the following equation. You have the electric and magnetic fields. This is r is that distance, and it's proportional to the ratio of the charge by mass of these cathode ray particles. Now Thomson did this experiment. E and B he could measure. R, of course, is the size of the apparatus, which he knew beforehand. So what he found is that when he found the cathode rays, he got a number which is like 1.6 into 10 to the 11. And whereas when he used ionized hydrogen instead of a cathode, he got, which is positive, he got an EMF of 9.5 10 to the 7. So the ratio about 2000 in between these two. And with this ratio, so see, there are two possibilities. One is that the charge of the cathode rays can be 2000 times that of the hydrogen. But then if you have such a high charge, after some time, the cathode will itself become positive because it's losing so much negative charge. The other is to assume that, okay, the charge is the same, but the mass here is much smaller. So that's why he concluded that the cathode ray particles must be at least 1000 times smaller. Well, actually it's 2000 times, so 1836 times smaller than the smallest atom. And so he called it the electron. So the electron was the first of the fundamental particles to be discovered. So the particle physics essentially starts from the discovery of the electron. Now, in roughly the same time, Becquerel discovered that atoms can emit radiation spontaneously. And you know the story, he had a paperweight made of uranium, and he kept it on a drawer on top of his plates, photographic plates, and he found that the photographic plates were ruined. There was an impression on the photographic plates. But the photographic plates were ruined, but he won the Nobel Prize for that. So it was a good bargain. Now, the Curies followed it up by the discovery of polonium and radium in the laboratory. They isolated these two elements. And of course, they are not the real people, okay? This is a still from the film, Madame Curie, which was filmed in 1943. Here are the real people. Okay, showing you that the casting wasn't too bad. Now, radioactive atoms disintegrate. So if something disintegrates, it breaks up, there must be something in it can't be an indivisible object. So if something breaks up on its own, then it must be having structure inside. And it was the classic experiments of Rutherford, you see Rutherford here, and Soddy, who was at that time his assistant, later became a professor in Scotland. So this is the famous experiment. You put a radioactive sample inside. When you open the top and you keep it in a magnetic field, you have three kinds of radiation. You have the alpha radiation, which is positive, that's why it goes in this direction. Beta, which is negative, goes in this direction, and gamma, which goes there. And they were able to show that the alpha particles are nuclei of helium, the beta particles are electrons, and the gamma particles, rays, are just like electromagnetic radiation. Okay, so that's... Now, Soddy and a gentleman called Fajans also correctly describe the nature of these radioactive transmissions. So if you have some element with atomic number and atomic mass number, Z and A, then if you have an alpha decay, it moves here, and if it's a beta decay, it moves here. They move and become different elements. So in the periodic table, this is called the Soddy's displacement law, or the Fajans-Soddy displacement law. So they move in the periodic table. So some actually change in the atoms happens. Now, if all this happens, they must be having a structure. Okay. So there must be some intention. So radioactivity is simply some atom, and that atom is breaking up. So we have to have a model of the atom. So the atom is not some indivisible solid thing like that, but there is structure. So the first person to attempt to have a structure in it was Sir J.J. Thomson. So what he suggested is, okay, there is a positive jelly kind of thing. You know, it's like a jelly, and then there are electrons set inside it. Okay. So he called it the plum pudding model. I'm not sure how many people in this audience have actually seen or eaten a plum pudding. It's not common in our cuisine. But you have eaten a laddu. And inside the laddu, there is badam and kismis. So embedded inside the rest of the laddu. So imagine it, call it the laddu model rather than the plum pudding model. Now this model looks good. The problem is that there is a theorem which was invented by the Reverend Samuel Earnshaw, maybe some 50 years before Thomson had thought of this. And this tells you that if you have static charges, if you take charges which are not moving, they will not be in equilibrium. They will start moving. So in fact, if you have this model, what will happen is that it will condense into little droplets of positive charge around the electrons, and eventually they will all fuse to give you a bunch of neutral particles. So the atom will not remain an atom, but it will disintegrate into tiny things. So Thomson or Earnshaw would have disintegrated, and so would you and me. Okay, the model cannot be the right one. Okay, solution came from the other part of the other side of the globe. It came from Hantaro Nagaoka, who suggested that the atom is in a state of dynamic equilibrium, like the rings of Saturn. See, why you've seen pictures, or maybe if you've seen through a telescope, you have seen the rings of Saturn. So why don't the rings of Saturn, why don't they fall into Saturn? Because they are rotating, going round and round. Okay, so he suggested that maybe the electrons are going round and round the central positive charge of the atom. And this he called the Saturnian model. So it's, as you see, the similarity with Saturn is very high. Okay. Now, from all these experiments and ideas, it's clear that atoms have some internal structure that they can break up. And so it is Rutherford, again, who set out to investigate the structure of the atom, to find out where is the positive charge, where are the electrons. So this is the apparatus he used. This is the actual apparatus he used. This is Rutherford. This is assistant Geiger, and this is their student Marsden. So when they did the experiment, as you would expect, it is Marsden, poor fellow, who took all the data. It is Geiger who collected them and drew the graphs, and it is Rutherford who wrote the paper. But anyway, so what did they do? So, they had the following thing. They had an alpha particle source. They had a thin gold foil and a zinc sulfide screen. So zinc sulfide, whenever an alpha particle falls on it, there's a little spark. Those sparks are the ones which Marsden sat and kept counting. Now, why gold foil? It's not because Rutherford was a rich man, but there's a reason for having gold foil. Gold and silver are the substances which can be beaten into very, very thin foil. They can be beaten very thin, even 100 atoms. So for silver, you of course know it. Okay, you've eaten it. All right. So, but for gold, of course, you have to be a Maharaja to do that. All right. So what was happening? Let's see a cartoon of this. So when particles came out of the alpha source, most of them just went undisturbed through the gold foil, or deflected a little bit. Okay. So that's what you would expect with the jelly idea of a jelly. But once in a while, you see, a particle started going backwards. Particle was thrown back. And this was such a surprise to Rutherford. And if you shoot a bullet at a jelly, what will happen? You don't expect it to come back and hit you. Okay. So he expressed his surprise in the following language. It was as if you fired a 15-inch cannonball at a piece of tissue paper and it came back and hit you. So clearly, the Nagaoka model or the Thomson model was not the correct one. There was something very strongly repulsive somewhere, but it had to be very small. So there must be some small place, that's why only a few come back. But that thing must be very strong. The repulsion must be very strong. It's like having a very hard core. So at once, the Nagaoka atom shrank. So this, instead of the electrons going around a big thing, it, like Saturn, now it became a tiny thing. So it became more like the sun and the planets around it. And Rutherford also realized that there's no reason for these electronic orbits to lie in the same plane. And why should they chase each other? Okay. So it could be different planes also. And that gives us the planetary model of the atom. So this is a model which you have in your textbooks. The electrons go around in orbits. And later, Bohr and Schrödinger discovered that, between them, they discovered that, no, there are some definite paths, and it's not really a path, but the atom consists, there are fuzzy orbitals. They are not exactly in the, like clean orbits, but there are regions of more probability and less probability. So that's basically a modern picture of the atom. That's what. However, the important thing to realize is that solid matter, the solid matter you're sitting on, which you consist of, your floor, all these things which look so solid, is mostly empty space. How empty, you will get to get an idea. So imagine that you blow up the nucleus to the size of a 10 rupee coin. Okay, it's there in your pocket, this size. Okay, in that case, the electrons will be about 2.5 kilometers away. So imagine, okay, here's a Google map of Bombay. TIFR is here. So imagine if the 10 rupee coin is here at TIFR, then the electrons are going around here. This is Gateway of India. So in between, there is empty space, nothing. Okay. So in fact, imagine a 10 rupee coin and let us say an even smaller object near Gateway of India. And the force between these is enough to hold it in place. So the force must be extremely strong, given the size. So atomic forces, in fact, are of mind-boggling strength. To take an example, if the atom had a 1% imbalance of charge, then you fold your hand. The force between your folded hands would be equal to the force required to hold up a large mountain. Okay, so that's the level of the strength of this kind of force. So next question. So we have the nucleus now. So is the nucleus a particle? So we come to this discovery of William Prout, who said that the mass of every nucleus appears to be, well, with some error, an integral multiple of the mass of the hydrogen nucleus. So the hydrogen nucleus is the smallest nucleus, and it must be a fundamental particle. And the name given to it was the proton, which is Rutherford who gave that name. And therefore, larger nuclei must be simply bunches of protons. You put lots of protons together, and that's the right. So the proton, let us say, was the second fundamental particle to be discovered. However, there is a catch in this. The charge of the nucleus is determined by the number of electrons, by the atomic number. And you can show from X-ray, I'll forget about these details, but you can show from here, you can find that the charge of the nucleus is the same as the atomic number. You can actually measure the charge. It was done by Moseley. And the problem here is that the atomic number and the mass number, so mass number is the number of protons, atomic number is the charge, these are different. Okay, take for example tin. Okay, tin has a atomic number of 50, so the charge on it is plus 50. And the number of mass number is 118. So you can ask the question, if there are 118 protons in it, why is the charge only 50? Where has the rest of the charge gone? So again, Madame Curie suggested the answer. She said, okay, there must be electrons inside the nucleus. So what number? Precisely 68 electrons, so that the charge cancels and you have got a charge of 50. And when you have beta decay, these must be the electrons. You know, they radiate. So radioactive decay, beta electrons come out of the nucleus. So these must be those electrons that once in a while they come out of the nucleus. This problem, the problem is that with the uncertainty principle, which, see, this was 1913, uncertainty principle came in 1926, Heisenberg's uncertainty principle. This shows you that if you put, you have an uncertainty in position and momentum, so the size is about 10 to the 13, these electrons must have much more energy. So the electrons which come out have about 1 million electron volts, but they should have energy of 1 billion electron volts. So clearly these are not sitting in, they're not coming from inside the nucleus in that sense. They must be created and immediately emitted. So same question. So Rutherford in 1920, very tentatively, he had suggested perhaps there are neutral particles inside the nucleus, but he wasn't sure. So nobody took this idea very seriously. But it was Dmitry Ivanenko, after applying quantum mechanics in 1930 to the nucleus, he came up with the said, yes, there are neutral particles, they are called neutrons, and we have what is called the proton-neutron number. So what is the number of neutrons? Precisely that's 68. So 68 neutral particles, and the rest are charged protons. So proton nucleus. And then in 1932, within 2 years, of course, when you want to look for something, you will find it. So, well, usually, he discovered this neutral particle and the neutron. So this neutron was the third fundamental particle to be discovered. So we thus obtained the atomic model, which completely explains the periodic table, is described in every textbook, which you have all studied. Now a new puzzle arose. See, in the nucleus, you have protons and you have neutrons. Now, the like charge, protons are like charged, they're all positively charged, so they repel. But neutral particles do not attract or repel. So what prevents the nucleus from flying apart? The protons should all fly apart. Now, that doesn't happen. Nuclei are stable. That's why we are all here. Otherwise, we would all have disintegrated into protons. So what happens is Heisenberg in 1932 suggested there must be a new kind of attractive force binding the protons and neutrons together. So basically, it must be acting between every pair of proton and neutron. There must be an attraction which is holding them together. And this is called the strong interaction. Let's estimate it. So suppose the nuclear force is given by the inverse square law. This is the charge of the two protons, and this is the radius size of the nucleus. So you can always divide and multiply by A naught, which is the size of the atom. So then this gives us the force between atomic force between a nucleus and an atom, or a proton and an electron. So I'll call it atomic force multiplied by this ratio. So this is the size of the atom divided by the size of the nucleus. And we happen to know this. The size of the atom is about 10 to the minus 8 centimeters. That's an angstrom. And this is about 10 to the minus 13 centimeters, otherwise known as a Fermi. And if you take the ratio, it is 10 to the 5 squared. So 10 to the 10. So the nuclear force is 10 to the 10. That's 10 billion times the atomic force. So it is immensely strong. So it is so now just imagine, remember the atomic forces alone can hold up things as large as the pyramids, okay? Why pyramids? Even mountains, whole mountain ranges. After all, they only sit on a layer of atoms at the bottom. So the atoms are not getting crushed. So that shows you that that's how strong the atomic force is. Now this fellow is 10 billion times stronger. So immensely strong. So obviously you call them strong interactions. Now, Yukawa wanted to build up a model of the strong interaction, and it is based on the model of electromagnetic interactions. So you look at this cartoon of two skaters. So what is happening? They're exchanging the ball, right? Now, if you couldn't see the ball, what would you see? You would say the two fellows repelled. They repelled each other, right? But it's actually the exchange of the ball. So we assume that charged particles interact by exchanging. The analogy of this ball is the photon. So what you can do is you can represent this whole thing on a space-time diagram. How does that work? So imagine these are two electrons, and you're plotting the distance on this axis, time on this axis. So let the two electrons come together. The plot is also going on at the same time. They exchange the photon, and then they go back. So you get a diagram like this telling you that this collision happened. So if you remove the axis, you get something called a Feynman diagram. So it is Feynman who taught us to think of these collisions by drawing this kind of diagram. And this, particle physicists use these diagrams all the time to understand their subject. Now, Yukawa said that the strong interaction of nucleons, they similarly correspond to the exchange of particles called pions. So there are different pions, charged and uncharged, which are exchanged between the proton and neutron. And of course, you can write them in terms of Feynman diagrams also like this. There are three kinds of pions. Now, the real reason why the nucleons stay bound is that neither of them wants to release the pion. They are both holding on to the pion. So in that sense, they're holding on to each other. So to understand this, I'll show you this nice picture of two dogs. So both are pulling on the rope. Neither of them wants to release the rope. So from far away, if you can't see the rope, you will see the two dogs bound together and going up, okay? You won't see them. So it's the same story with the pions. Now, how to see these? So I bring you to the subject of cosmic rays, and of course to our founder of this institute, Homi Bhabha, and his collaborator Walter Heitler. They showed that cosmic rays are high energy particles bombarding the Earth's atmosphere, and they create showers of particles. So all you have to do for these new particles is to send up a balloon with a cloud chamber or something tied at the bottom. You take a lot of photographs, you bring your balloon down, and you have a free laboratory for particle physics. It's all happening up there anyway. You just go and photograph what's happening. Now, so you get actually beautiful pictures like this, and I'll skip this part. But you can ask, why are we talking about high energies? That comes from this gentleman who told us that E is equal to mc squared, that creation and annihilation of particles is possible. Energy can be converted into matter, matter can be converted to energy. Now, how does that work? You imagine that there is a heavy particle. It can decay into two light particles, and the heavy mass of that particle gets converted to the energy, to the kinetic energy of these. Let me repeat it. So they go out with high energy, high velocity, the kinetic energy takes up that excess. Now the opposite can also happen. Take two light particles with a lot of kinetic energy and put them together, they will create the heavy particle. So this is possible thanks to relativity. And that is where Yukawa said, okay, high energies, look for the pions in the cosmic rays. Go and look for them there. So people started it, and very soon, Anderson and Niedermayer discovered a particle of mass 100 MeV, which was initially thought to be Yukawa's pion. Again, it was Homi Bhabha who pointed out that if you had a pion which was strongly interacting, it would never reach the ground level. But the muons can be detected. If you put a muon chamber right here, it will start detecting muons. So how do they come here? So the actual particle is more like a heavy electron than Yukawa's pion. And eventually we call it the muon. It's a different particle. And nobody expected it, okay? So it was the fourth fundamental particle to be discovered, but nobody expected it. So in fact, the Nobel laureate Isidore Rabi, he said, who ordered that? We didn't ask for it. It just came. Anyway, this was 1937. In 1939, Hitler drove his tanks into Poland, and the Second World War began. Now, during the Second World War, there was not much scientific research because most of the scientists had been called away to work on weaponry and weapons. And of course, we know the most dramatic result of that. It ended up with the discovery of the nuclear bomb, or the invention of the nuclear bomb. So indeed spectacular when it happens. So, but you must remember that when this is applied to human beings, that's what happens. Okay, just to tie it up with this talk, the energy utilized in this arises from the strong interaction. So after the Second World War, fundamental research picked up again. Scientists came back to their jobs, to their universities, to the laboratories, and started working on fundamental theories again. And very soon, the real charged pion was discovered in cosmic ray showers in 1947. And here is the reaction. A pion is created. It decays into muon and a neutrino. The muon again decays to the electron and two neutrinos. You can't see the neutrinos. So the pion, muon, and electron leave tracks. Now let's look at these tracks. Here is the pion, here is the muon track, and here is the electron. So you clearly see the structure. So you see, it doesn't look like momentum was conserved here, but that's because there were two neutrinos here. Some neutrino coming out here. So it was actually discovered. And well, you see that you started with the electron, proton, and this was before the Second World War. And after the Second World War, not only did you discover the pion, but you started discovering more and more particles. So again, almost every year, just like the story of the periodic table, every year some new particle was discovered. Okay, it continued. I have stopped this list, I think, in 1964. But today there's a particle data group which keeps track of it, and there are more than 300 particles. Now you can see that this is again similar. See, if there were only a few particles making up atoms, that would be nice. It would be close to the Greek idea of unification. But if you have 300 particles, then you're gone. It's like the same situation as before. In fact, this was so messy that Enrico Fermi, you may have heard of him, he said, if I was able to remember half the names of all these particles, I would have become a botanist. Okay. So clearly the question to ask is, are all these particles elementary? So are we repeating the story of the periodic table? So history indeed did repeat itself. Such numbers of particles, of course, when you have a lot of things. See, in botany, when you have many things, what do? You have a classification scheme. You classify things into genus and family and so on and subspecies and write long Latin names for that. But for particles, we don't write Latin names, but you would want to classify the particles. Okay. So this classification, and if you do see a repetition of properties, same law, that indicates there is substructure. So this was actually done by these two gentlemen, Gell-Mann, Murray Gell-Mann, and Yuval Ne'eman independently. And they hit upon the idea that if you classify particles by two conserved quantum numbers, isospin and hypercharge, you can put them on graphs like this is isospin, this is the hypercharge, and this is a bunch of particles which are known as the pseudoscalar mesons. And what you find is that you can draw this nice hexagon and two particles inside. So there are 8 of them, which you can put in this fashion. All right, fine, you can put 8 particles, any particles into some shape. But when you take the set of octet vector mesons, lo and behold, it's exactly the same shape. So they have the same structure, same set of quantum numbers. And when you look at what are called the baryons, which includes the proton and neutron, again, you have the same shape. So these octets seem to keep repeating themselves. Isn't that like the periodic table? So Gell-Mann, who was a very well-read person, had read a lot about Indian theories and philosophy, he called it the Eightfold Way, after the Buddha. Of course, this has nothing to do with the Buddha's Eightfold Way, which is a way of living, okay? But he just called it the Eightfold Way, and that's the name by which it goes today. Now, the point is that what the Eightfold Way actually fits in very well with the idea that the strong interaction has a symmetry, don't forget about the name, that there are actually 3 quarks, 3 particles forming a triplet, 3 basic units, which I call V1, V2, and V3. And they're the antiparticles which are V1 star, V2 star, and V3 star. So it fits in well, but the charge of these will be 2/3, -1/3, and -1/3. Okay, so you can combine these units. So you can put 3 of these units together, and you will get everything corresponding to the proton, neutron, and the particles in this octet. And so this proton, neutron, and all the rest. So forget that detail. You can also form them into something called a decuplet, which looks like this. So there are these particles which had all been discovered, 9 of them, but there was no particle corresponding to this. So Gell-Mann said you can have a particle which goes there based on my 3 V1, V2, V3 units. And if you do that, he called it the omega minus. Well, omega is the last letter of the Greek alphabet, so this was the last particle to put in. So he put it there, and it's negative in charge. Now, in 1964, the omega minus was actually discovered. So you see, this is a repetition of the story of Mendeleev. Mendeleev created the periodic table. He used the properties of the periodic table to predict new elements, which were then discovered. So Gell-Mann used the properties of the elementary particles which existed to predict a new elementary particle, which was discovered. So with this, people started believing, and he then went on to claim that these fictitious units, which I had called V1, V2, they are real particles. So he called them quarks. Why quarks? Because at that time, he had got a lot of negative feedback from other scientists who didn't believe his theory. So there is this little poem in Finnegan's Wake, 3 quarks for Master Mark, that's himself. Sure, he hasn't got much. 3 quarks means quacks, okay, by a duck. So there are 3 ducks saying it. Anyway, so he called them the up, down, and strange quarks. Okay. So these baryons are now bound states of 3 quarks instead of V1, V2, V3. And the mesons are quark, anti-quark bound states. Now, one important feature about these is that the force between them is so strong that you can't isolate them. Why is that? So imagine that this is a potential. Okay, I've drawn it sideways, and there is this meson quark anti-quark pair which are bound into this. Okay, the potential goes up like this. So what happens if you try to bring them apart? Then the energy increases, right? This is the bottom now here. Now it has gone up. The bottom is here. So there is more energy in it. So if you want to bring them further up, the energy will have to increase further. You'll have to put more energy into it. Now at this point, because of relativity, it is energetically more favorable to create a new quark anti-quark pair out of the vacuum, to create a new pair rather than to pull them further apart. So what happens is these new pairs are created, and you again have 2 pairings. So essentially you end up with 2 different mesons. So 2 copies of the same thing. So what you see is a meson decaying into other mesons. So this is similar to what happens if you try to tear apart a bar magnet. What would happen if you try to extend a bar magnet? The beginning it will extend elastically, then it will break in the middle. In the middle, what would happen? Again, you would have a new north pole and a south pole. That shows you that you cannot isolate poles. Similarly, you cannot isolate quarks. So that's called quark confinement. Now you can ask this question, why should we believe? Again, in the existence of quarks, we can neither see nor photograph them, we cannot separate them out. So why do we believe in this existence of the nucleus, which is too small to be seen or photographed? The reason is, what did we do? We sent probes inside the atom, and that was Rutherford's alpha particles, and inferred the existence of nuclear from the scattering data. So let's do the same by sending electrons, very high energy electrons, inside the proton and see how they scatter. So this is the formula, but don't worry too much about it. There are these 2 parameters in this, W2 and W1. And if the proton is a point, then these are 1. So an actual graph would be like this, that as the electron energy increases, these 2 would be 1 if the proton is like a point particle. And if the proton is like a jelly, like the Thomson jelly, then it would go down fast with energy. This really means that when you go down, nothing scatters. It just goes straight through. But in fact, when people did the experiment, they found that in the beginning it's behaving like a jelly, but then it sort of flattens out at a value around minus, so about 1/3. At 1/3, it is starting to behave like a point particle. Remember that this is a probability. So the probability of it being a point particle is 1/3. What does that mean? So this experiment was actually done by these 3 gentlemen. They won the Nobel Prize for it later. But more important is the fact that these level off at 1/3 means that there are 3 point particles inside. The probability is 1/3 of picking up each of them. So 1/3, 1/3, 1/3 will give you the probability of scattering from the proton. And these Feynman call them partons, but they are the same as Gell-Mann's quarks. So we have what is called the quark parton model. So now we know that there are actually particles inside the proton. So today we know of these are the 3 quarks of Gell-Mann. We know of 6 quarks. So another one was discovered in 74, one in 77, and the last one in 1994. So we have reason to believe that there are no more. So this may be the full component of quarks. However, there is some repetition in the properties. I mean, you can pair this pair behaves like this pair behaves like this pair. And similarly, we have 6 leptons, of which the electron and muon I have mentioned, the neutrino, and then there are others, muon neutrino, the tau. So we have good reason to believe that there are no more. But again, there is some repetition in the properties. So what did I say? Repetition in the properties indicates substructure. It is something deeper. So the $1,000,000 question is there more substructure? So there are two approaches to this, both of which are now 50 years old. One came up in 1974 by Yogesh Pati and Abdul Salam. They suggested, okay, now we repeat the same story. Maybe the quarks, leptons, all of them made of 2 or 3 smaller particles, which they called preons. So perhaps that's what's happening. It's just a repetition. There's another layer of smaller particles inside. A different but also very interesting idea came up with Shirk and Schwartz same year, and they said, no, there is only one thing. There's tiny strings, and the different oscillation modes of those strings correspond to the different particles. So now you see, this is very similar to the idea of Democritus. So the ghost of Democritus must be very happy that, again, there is only one, and it is, instead of multiplicity of structure, it is multiplicity of oscillation modes. So same idea, but coming back in a different form after many centuries. However, some issues still remain. And one of them is, in addition to electromagnetism and the strong interaction, there is a weak interaction, which is weak at low energies, but at high energies it unifies with electromagnetism. Now, weak interactions are crucial to understand many things. Why left-handed and right-handed are different, and why is that? Secondly, why is there more matter than antimatter? Because of course, if there had been equal amounts, we would all the time annihilate into gamma rays, which we don't do. Everything you see around you is matter. And finally, the nature of dark matter, which I will come to a little later. So there's an electric unification model of Glashow, Salam, and Weinberg. And what it basically says that high energies, there are 4 exchange particles, the photon, 2 Ws, and a Z, all have 0 masses and the same interaction strength, and the theory is unified. But when the energy drops below around 250 GeV, a sort of phase transition occurs. The Ws and the Z acquire masses, and their interactions become very feeble. They become weak interactions. The photon, of course, doesn't acquire a mass, remains massless, and it gives you the electromagnetic interaction. Okay. At very high energies, the quarks and leptons are also massless. They also acquire masses through this phase transition. So what is this phase transition? What happens in the early universe? Well, this is where Mr. Peter W. Higgs comes in, Professor Higgs. And what he told us is that we require a new particle to do this job, for this phase transition. So we have a spinless particle, which is also known now as the Higgs boson. And it is the Higgs boson itself which undergoes a phase transition. And this induces phase transitions to all the other particles except the photon. So the Higgs boson thus gives masses to all the other particles. Okay, having acquired a mass by itself, it gives mass to the other particles. Now, this was crucial because if all the particles were massless, relativity tells us that a massless particle moves at the speed of light. 2 particles which are both moving at the speed of light, their relative velocity is also the speed of light. So all particles will be moving at the speed of light. Nobody would ever talk to each other. You couldn't form any structures at all. But of course, structures have formed in the universe. We have galaxies, we have stars, we have planets, we have ourselves. We are all structures which formed. So therefore, we all have mass, and that mass must have been formed. So it is Higgs which has given masses. It is Higgs which permitted the universe, as we see it, to form. And that's why media love to call it the God particle. But of course, other gods, so it's not the only God. So it took 48 years to find the Higgs boson. So eventually it was found at the LHC in 2012. So the LHC is a giant machine on the French-Swiss border. It makes protons collide head-on with other protons. And some of the energy of the collision is converted into new particles, just like I showed you earlier. So here is a cartoon of what LHC does. You have you have to say this is the collision point, okay? And at this point, 2 protons come in from both sides. And once in a while, they create a Higgs boson. So once every 3 lakh collisions, a Higgs boson is created. Now, Higgs boson is unstable. It immediately decays to lighter particles. And then those lighter particles again decay to even lighter particles, which are stable. So eventually you see 4 particles around. And from those 4 particles, you infer that a Higgs was discovered. So here is an actual event simulation from the CERN collaboration. This is Higgs going to 2 particles called the Z and Z star, and then they decay to 4 muons. So these are the muons you see. From here, you can reconstruct and say that Higgs was discovered. And that's how the Higgs discovery happened. So these 2 very happy-looking gentlemen won the Nobel Prize in 2013. This is Higgs. This is François Englert, who wrote a very similar paper to Higgs in the same year. And this is the poor Robert Brout, who wrote the same paper with Englert, but unfortunately he died 1 year before the So if you want to win the Nobel Prize, you need to live very long. So good thing is that both Peter Higgs, who is now 94, and Frosty-Ongler, who is 91, they are still alive and well. So anyway, so the Higgs boson was the last ingredient in the Standard Model, and finding it has made the model complete. So we have the quarks, we have the leptons, we have the intermediate particles, and the Higgs was the only one left. And this has been tested to an accuracy of 1 in 1 lakh. So that's really, really good testing. So have we achieved our goal? Are we done? Sadly, the answer is no. There is no dark matter in the Standard Model. So a little bit about dark matter. So consider a neighboring spiral galaxy called M33. Okay, it's a spiral galaxy. And the galaxy is actually not static, but it's rotating slowly. Okay. Now, as it rotates, you can measure the speed of rotation. And you can see how that varies along the radius. So these measurements were done by Vera Rubin in the 1980s. And what you would expect, if all the mass was concentrated where you see the light, what that you would expect the graph to go like this. This is just an application of Newton's law. But it doesn't go like this. This is what is observed. It sort of stays flat. In fact, it increases a little bit. So there must be a lot of matter here which we are not being able to see. So that says that every galaxy has a halo of dark matter. And as you go further, you are involving more and more of the dark matter. So that's why the velocity keeps on increasing. Now that's a surprising result. But the problem is there is nothing in the Standard Model to explain dark matter. Now, of course, you can do this for a neighboring galaxy where you can measure the rotation curves. How do you see far away dark matter? Well, there's a phenomenon of gravitational lensing. I'll quickly explain that. See, imagine there's a star here. This is our Earth from which you're observing. And there's a lump of dark matter here, okay? Even this line should not be there. I'm just showing it, otherwise I can't show it. Now, when light comes to the Earth, towards the Earth, light from the star goes in all directions. But some of the light is bent by the gravitational force of this dark matter. So bending of light occurs in Einstein's general theory of relativity. But when it bends and comes to us, then it seems that the star will be coming from here, right? You learned optics. So if the light comes in one direction, the star seems to be that direction. But it can also bend around the other way. So the star can also seem to come from here. And this can happen all around. So you would see the image of the star all around, not one point, but just a circle like this. So if that is the dark matter here, what you should see is a ring around it. Star should look like a ring. And of course, it's not perfect because there are clouds of gas and dust in between. So essentially, you see a broken ring like that. So that's the kind of Einsteining you expect. And I'll show you a very perfect picture, which was taken last year by the James Webb Space Telescope. You see this almost perfect Einstein ring. So this is actually a star somewhere behind that. So it's a real phenomenon. It tells you about the existence of dark matter. So what can dark matter be? Can it be things like black holes? Can it be things like, dead stars which are not radiating? Answer is no. It cannot be ordinary matter. And this is an example of a cluster of galaxies. So the naked eye picture doesn't tell you much. But when you look at it from the X-ray, then you get a picture like this. So the Chandra X-ray observatory showed that actually the ordinary matter is like this. And here is the dark matter around it. So you notice something, the dark matter is almost spherical or elliptical. This is very irregular. So what this means is that two galaxies, which were originally sort of spherical, each had a halo of dark matter, they collided. When they collided, the ordinary matter got distorted. It interacted, they got distorted, and that's why you're seeing these distorted things, But the dark matter nothing happened. Dark matter didn't interact with any of them. It just passed through. Didn't have the same interaction there. So therefore, the particles which make up the dark matter are not interacting in the same way as the other particles. Okay. So therefore, the only they have to have gravitational interaction, but that is not strong enough for them to form in the first place. So the only interaction left is the weak interaction. So gravitational dark matter must have weak interactions. That's why I told you weak interactions are needed to explain dark matter. And that is also true if you study the fluctuations in the cosmic microwave background. That's a more technical thing. But what it really tells you is that the universe is composed only of about 5% of ordinary matter. So everything I've told you about is only 5% of the universe. And there is dark matter, which is about a quarter. And all of the rest is some 2/3, is some strange thing called dark energy, which we don't understand. So the standard model, all I've talked about till now, very proudly, is only this. So that's a humbling thought. So if the dark matter is not some ordinary matter, it must be some new kind of particle. And so where would you look for a new particle? Well, we have this wonderful collider, the LHC. So we look to the LHC to discover such particles. And I should tell you that HC has run for about 10 years with a two years gap in between because of the lockdown. And so it has only barely started searching. It's going to run till 2040. Okay, so I may not be around 2040. Younger people surely will be. And it has barely started searching. So this search is going to go very deep. Okay, so eventually, and hopefully we will find these new particles. So stay tuned. So you will see a new particle at some stage. So to conclude this talk, we have come a long way in our understanding of the way in which nature works. Okay, it's a long way. We remember started from grinding things in a mortar and pestle. And what is amazing is that though nature is so complicated, the basic principles are very simple. And that brings us to this famous comment of Einstein: the eternal mystery of the world is that it is so comprehensible. We can use the same laws to understand the atom, to understand galaxies, to understand the universe as a whole. It's amazing. The same principles occur everywhere. So that is the real mystery, that how is it that only a few principles build up this great and complicated universe of ours? So that's something to think about. And on that note, thank you. And I think my talk.
Thank you, Shrirup, for that wonderful talk and the journey through the history of physics, particle, and everything. So now the podium is open for questions.
Thank you, sir, for the wonderful talk. One of my thoughts was like when you talk about fundamental particles, they should they also be stable in existence, because like only electron out of all your fundamental particles exist as stable independent particle. Rest all are just combination. Can you just comment on that?
Well, what we understand to be fundamental particles are particles which are the basic ingredients of matter, okay, of matter. And when we mean matter, we also mean matter in the early universe, okay? So these particles, let us say in the early universe, they were stable. After they've acquired mass, they are unstable and they can decay. So in that sense, they are fundamental. But yes, so we distinguish between fundamental particles and stable particles. The point is that if you only look at stable particles, then you only have the proton and the electron and the neutron, let us say. Neutron is also not stable. It decays. So if you have only the proton and the electron, then of course, if you limited particle physics only to that, then we would stop, let us say, 1911. Okay. All the progress we have made of understanding. So ultimately, what do we want to understand? We want to understand what are the basic things. So the deeper levels of substructures. We do not know if, see, some of the quarks are stable, some are unstable. So this whole understanding is based on the understanding of what happened in the early universe. At that stage, we look at fundamental particles.
Also mentioned that most of the quarks are also thought to be only vibrations. So all the fundamental particles would only be vibrations. So does it like can we compare it to the Indian philosophy of the entire universe is just energy or vibration or what?
So to tell the truth, I'm neither an expert in string theory nor an expert in Indian philosophy. Okay. Now there is some, I mean, you can draw analogies between that and several other philosophies also. So I would say that string theory came from one aspect. There is some similarity of that. Indian philosophy looked at it from a different aspect. And this is what I would call a superficial similarity. You can find similarities if you go to Chinese philosophy, if you go to any other ancient philosophy. There are similarities in the ideas because human beings think in the same way. So I wouldn't call it a relation between the two, but there are always some similarities in the ideas. So I would stop at that point. No question there. Question there. Okay. Sure.
You said that the dark matter particles may not be part of the standard model particles.
Not may not, are not.
Are not. So if you, using LHC, for example, if you are colliding standard model particles, how do you expect it to create dark matter?
Very good question. There has to be a mediating particle. There has to be something else which interacts both with the standard model and with the dark matter. Okay, but see, if those particles were not there, then how did the dark matter form in the early universe? See, the dark matter didn't interact with anybody. Eventually, it has to be connected to photons, right? Photons were what the early universe consisted of. So the dark matter to come out of those photons, so there has to be a mediator. Maybe it goes to standard model, maybe it connects directly with the photon. Either way, we should see that interaction.
And the interaction that we know that it definitely interacts with gravity, and then with standard matter particles, it will be some kind of weak interaction. Do we know that interaction?
The point is that if it was only gravity, you would not produce the proper relic density. You would not produce enough. So there has to be one other interaction. It can't be the strong interaction because you see the bullet cluster, it didn't disintegrate. It can't be electromagnetic interaction because then you would see radiation. So you're only left with the weak interaction. That's the logic.
Two questions.
Yes.
First one is, you mentioned as a property of fundamental particles to be spin. So is that like normal angular momentum spin like in classical mechanics, or is that something else?
Well, the answer is both yes and no. It is like angular momentum in the sense that it has the same dimension, you can add it.
Yeah.
But it is not actually a spinning object because these are point particles. A
Yeah.
point cannot spin. So when you learn quantum mechanics, you will know that in quantum mechanics, you can have angular momentum of a point particle also.
Okay.
So that spin is that kind of an object.
Okay. My second question was, like, using the Feynman diagrams, you described how electrons are repelled by each other.
Yes.
How do you describe attraction with that?
Okay. You can have a similar diagram. Okay. The diagram is the same. The equations will give you an attraction. Okay. Now, if you want to do more, it has to be technical.
Yeah.
But yes, it works both ways. I can just see for the pions, it's an attraction.
Hello, sir. Here.
Yes.
Sir, in your storytelling, you have mentioned Richard Feynman, and at that time, even we are in TIFR and Homi Bhabha and all. This is typical Indian storytelling where we conveniently, ignore or don't mention J. Wheeler, because that I realized because I myself graduated in around 2007-8 as an engineer. And so what is the reason why we conveniently ignore or don't mention him? Because he was alive up to 2008.
You mean, whom are you referring to? John Wheeler?
Yeah, Wheeler, yeah.
So Wheeler's contribution to this thing is more contribution to nuclear physics. It is essentially the Bohr-Wheeler theory, which is called the liquid drop model, which is useful for fission. So in a sense, when I showed you that picture of the atomic bomb, okay,
so that's why
there was Wheeler behind
Hiroshima, Nagasaki. You had a slide on that.
Let me finish. There was Wheeler behind it. But most of Wheeler's contributions were in a different direction. They were mostly in cosmology and gravitation. So since I didn't talk about that, in particle physics talks, John Wheeler, if I was to refer to John Wheeler, I have to refer to another 20 scientists also. Okay, see, I have not mentioned many famous scientists. I have not mentioned Max Born, I have not mentioned Pauli, I have not mentioned Dirac. I mean, all of them contributed to this. Okay, I just mentioned the main names. So it's not that I have any dislike for John Wheeler, great respect. He was a great scientist. But his name was not, there was nothing of what he did, of his great body of work, which is particularly relevant to this talk. That's why I didn't mention it.
Sir, another question, it's a separate question. So in the mechanics of small particles, quantum mechanics, the psi that we all learn about, it comes from the continuity equation in electrodynamics actually. So
No.
Yes,
it describes the probability of finding a particle.
No, that is in the textbooks.
Oh,
yeah.
Well, I have only read textbooks.
Okay. We'll speak later.
Good evening, sir.
Yes.
Sir, two extremely layman questions.
Yes.
Like it's said that energy is neither created nor destroyed.
Where are you? Can you raise your hand? Okay. Yes, please. Go ahead.
Why am I not visible always?
Yes.
Sir, good evening, sir. Two extremely layman questions.
Yes.
Like it said that energies can neither be created nor destroyed. So where are we getting this energy from? And the second one is like, since we have been talking about darkness and dark matter and all these things. So nowadays there is a buzz that even darkness has a speed comparable to as to light or speed of light. So
Okay, let me answer the first one. So that energy can neither be created nor destroyed is good at the energies of the laboratory, typical laboratory energies. If you have a tabletop experiment, laboratory energies, that works well. However, when you go to higher energies, this does not work. Einstein's special theory of relativity tells us that energy can be converted into mass and mass can be converted into energy. And of course, the greatest example of that is nuclear energy, where mass is actually being converted to energy. So that logic holds at low energies. What is the threshold? Till you have enough energy to create a new particle. So the lightest particle we know is the electron. So to create the electron, the energy you need is 511 kilo electron volts. So that is far above the energy you have in the laboratory, in the typical experiment in the laboratory. So for that, you have to build a high energy machine. So that's where it occurs. In nuclear science, yes, you are creating energetic particles all the time. Particle physics, that is the bread and butter of the subject. So that is a aspect, is a theory which works in the school laboratory, the college laboratory, it works well. The next question you asked about the speed of dark matter, we don't know. If it has mass, it won't move at the speed of light. If it doesn't have mass, it will move at the speed of light. But you have to discover it first, okay? See, if I've never seen a person, how do I know how fast he runs? Okay, we discover it. Once we discover it, we'll have an answer to that.
Sir, sorry, sir. Another question is like,
Yes.
just like we keep asking whether it is the egg or the hen first. So are we living in dark or the light is living in the...
The light is what came out first, no question.
Thank you, sir.
So you see, God said, let there be light, there was light. The Big Bang said, let there be photons, and there were photons. Everything else came out of that.
Any other questions?
Just one minute.
Sir, about the dark matter,
Yes.
the speculation of the dark matter was because of the M33 rotation, right?
To begin with.
To begin with. So it might be that the reasons might be different than other than dark matter.
Yes.
And were there any supporting other scenarios where they speculated that dark matter can exist?
Well, it does support, because you see, the gravitational lensing is a different phenomenon. It is not obtained by looking at Doppler shifts. It's obtained and looking lensing phenomena, okay? So there are very many others which satisfy, not very many others, maybe 3-4 different things which all hint towards the existence of dark matter, and they're all consistent with each other. That much I can tell you. But as I see, until we discover something which we can identify as dark matter, we won't have the full answer to your question. So it's very much a very hot area of research.
Thank you, sir.
Do we have any more questions? Okay, so now we have one more.
Could you shed some more light on dark energy? What it is hypothesized to be?
It's dark, I can't shed light on it.
Why was
I
it
just-
hypothesized?
No, I'll just tell you a little bit. So, long back, the universe was discovered to be expanding. That's why we think there was a Big Bang and it's expanding from there. Now, most of the theories we had about the Big Bang were that if you have normal matter, then either it can go at uniform rate of expansion or it can slow down. In fact, the measurements made around the year 2000, maybe a year before and after, they showed that the opposite is happening. It's actually accelerating a bit. So that means that if it slows down, that means things are pulling back. If it goes uniformly, that means it's just the forces are too weak to stop it. But if it's accelerating, there's something pushing it out, behaving the opposite way to gravity. Now that behavior you can have if there is some uniform density of something or there is some matter which repulsion. It's not known. We haven't seen anything which corresponds to that. So it is just given name dark energy. It just, you can as well have called it unknown effect. So that's why I said we know very little about it. Of course, you can have a theory, you can have a speculation, but there is no hard evidence, either observational or experimental, for the nature of dark energy. But we know that it has to be there because what else is pushing the universe? That's that.
Thank you.
That's the only light I can shed on this.
I have a question.
Yeah.
So, is dark energy also similar to what we find in black holes?
Well, I don't know the answer. I don't know what's inside a black hole. But normally black holes are formed by the collapse of ordinary matter. Ordinary matter like stars and so on, which are perfectly visible, which have all the interactions. And that forms a black hole. Once it's formed a black hole, no information comes out of it. So we don't know what's happening inside. But perhaps nothing happens inside. Perhaps the people inside the black hole, they don't know. We are the black hole to them. Okay. But whether it's connected with dark energy, really, it's a question which there is no answer at the moment. And maybe a black hole collapses, taking a part of dark energy with it. If you knew the nature of dark matter and dark energy, some of that may go into the black hole also.
Hello, I had a question.
Yes.
So like you told that, we have started the particle physics, like from alchemy, we have started to manipulate substances and everything.
Well, long before alchemy.
Yeah. So we have we used our, known perception of the world to create meaning out of it. And in the course of discussion till the end of the lecture, we conclude that yes, there was dark energy also, and there are more particles that do not fit the standard model.
Yes.
So I wanted to ask that since when did we understand that there is something called dark matter or dark energy, and when did it start to occur? Like when you told that when the universe started, the photons have come, but when did dark matter, dark energy form?
Very early in the universe, there are, again, see, until you know the exact nature of interaction, you can't tell at what point. We can tell at what point ordinary matter formed. Okay, because we know how it interacts. The dark matter, dark energy, we know that they formed in the early universe, that they didn't form after some time, which is called the freeze-out time. But exactly what point, we don't know because we don't know the nature of that interaction. The other question, if you ask about when it came into science, so dark matter was calculated in 1938 by an astronomer called Fritz Zwicky, and it became much more concrete with these measurements by Vera Rubin, which were done in the late 70s and 1980s. And lensing came later. And dark energy was a big surprise. It was not expected. Only in the late 98 and maybe within 2 years, suddenly when people looked at very far off supernovas and discovered that they are actually accelerating rather than slowing down, it was then that the concept of dark energy came in. Okay. But of course, it had been there from the early universe. Okay, so that's only when we started thinking about it.
So the concept of dark matter was already in theoretical physics way before, and then when the lensing effect was observed, it was confirmed.
Well, you see, everything creates lensing. Sun creates lensing. Even you and I are creating a little bit of lensing. Okay, very more, but not measurable, but it's there. But when you see lens in between, okay, suddenly you see a ring, the middle of the ring, then of course that must be dark matter.
Thank you, sir.
Yeah.
Okay, so with this, I think we should thank the speaker once again. So,
thank you.
Yeah, I thank everyone for coming to this occasion on National Science Day. And there is tea and snacks outside. You can go and enjoy that. Thank you. Thank you, sir. It was really wonderful. Sorry about the mess up with the talking thing.
Most people are outside.
Okay. Yeah. Absolutely. I mean, I could see that. The thing was they wanted to confirm whether there was video or not. It's about live streaming.
If I did, I would have really take out the connections.